Introduction to Enthalpy, or Entropy, Lecture 25. So the last time we introduced thermodynamics, and we talked that there was this thermodynamic property called enthalpy, or the heat. We talked about changing energy. Now we're going to introduce this new concept, or some additional thermodynamic variables, the first one being entropy. So let's start by thinking about what we call a spontaneous process, or a spontaneous chemical reaction. So those are things that happen without us actually doing anything to the system. So here's a list of some things that are spontaneous, water running downhill, a lump of sugar dissolving in coffee, water freezing below 0 degrees Celsius or melting above 0, heat flowing from a warmer object or hotter object to a colder object, what we discussed the last chapter, gas expanding inside this vacuum, or iron forming rust. All of these processes happen without us actually doing anything to it. Right? We can see down here at the bottom two other spontaneous reactions where we take a gas and we fill a gas on one side, we open a stopcock, will allow it to expand to both sides of this, and it won't go the opposite way, so we won't have gas. It's separated between two. It's not going to spontaneously go to only one side of that container. Or if you go skiing, you ski downhill spontaneously, you don't ski uphill spontaneous. So we have these two different processes: spontaneous, it's going to occur without us doing anything to it, or non-spontaneous, that we have to actually do something to it. And we see typically these are opposites. So a spontaneous reaction will go forward without us doing anything in it. A non-spontaneous won't, but then a non-spontaneous will go in reverse spontaneously, or vice versa. Right? So let's talk then a little bit about what this has to do with what we've talked about so far, this enthalpy. Does the enthalpy directly relate to whether this reaction is spontaneous or not? So here's a series of reactions, and notice that we're given their delta H values for all of these reactions here. So we can see for methane, combustion of methane, we get carbon dioxide and water, we get a negative 890.4 kilojoules. When we combine H plus and OH minus, again, spontaneous reaction to form water. We use that when we balance redox reactions. You get a delta H of a negative 56.2 kilojoules. If we look about water going from a solid ice to a liquid at 25 degrees, this is spontaneous, right? So, but it has a delta H value of 6. It's a positive number now. If we look at ammonium nitrate dissolving, it's soluble. Remember our rules of solubility. So it's going to break into its NH4 plus the ammonium ion and the nitrate ion. But again, it has a delta H value of 25. Again, positive. So you can see all of these processes are spontaneous. They occur on their own. But we have two different signs of enthalpy. So it means that this enthalpy value does not really give us any information on whether a reaction is spontaneous or not. So we have to have some other variables in order to understand if a process is spontaneous. And that's what we're going to learn about in this chapter. The two other values that we're going to look at is entropy and then Gibbs free energy. We'll spend some time today talking about what entropy is. Next time we'll talk about how to calculate or do some calculations with entropy. And then the final lecture we'll talk about Gibbs free energy. So let's go back to the law of thermodynamics. The first law of thermodynamics, which we talked about and based all of our discussions on in the last chapter, is that energy cannot be created or destroyed, but it can converted between one form and another. Right? So when we talk about these changes in energy, the energy of the system or the universe has to be equal to, or the change in energy of the universe has to be equal to 0. So we can follow those heat transfers using calorimetry and whatnot. Now we're going to start talking about this second law of thermodynamics, which says the entropy of the universe increases for a spontaneous process and remains unchanged for an equilibrium process. Right? So, just in nature here. Right? So, we're always looking at this process. If it's a spontaneous process, the entropy of the universe has to increase. Right? But let's spend a little bit of time talking what entropy is. Entropy, which we're going to abbreviate as a capital S, is a measure of randomness or disorder, or chaos, if you will, in a system. Right? So if order increases, become more ordered, then our entropy is going to go down. If it becomes more disordered, our entropy is going to increase. Right? So if we're looking at changing these in a reaction, we're looking at changing the amount of disorder. So if our entropy of the final state is greater than the entropy of the initial state, then delta S is going to be positive. And since we're talking about disorder, the more structure or order we put on a compound or a structure, the smaller value of S entropy is going to be. Notice we can't have negative values. Right? This is more of a continual system where we can have a zero value, or we can have positive values. We will not have negative values of entropy. Our more ordered state is going to be the solids, so solids always have the smallest value of entropy. Liquid is going to be more disordered, so it's going to have a larger value, and gases are the most disordered, so those are going to have the largest values of S or entropy. And as we go from those states, those changes are going to be positive, as indicated here. So let's break down then this entropy a little bit more and talk about sort of the way we conceptually think about entropy as being this. Right? We can calculate entropy as being some constant K times the natural log of W. W is the number of microstates. So we can think about these microstates as shown here as the number of different possible arrangements we can have for this molecule or this system. Right? So if we look on this side of the table, we can see that when we have a closed system, there's only one microstate possible. All those molecules, whether there's one molecule, two molecules, or three molecules or atoms, they can only be in one arrangement, in that one side. So they all have the same number of microstates, right? 1. If we open up those two sides, now we can start increasing the number of possibilities. So if there's one atom, we can see that there's either going to be the atom on one side or the atom on the other. Right? So we give us 2 microstates, 2 possible arrangements. If there's 2 atoms, now we have a possibility of 4 different arrangements. They can both be in one side, they can be separated, but the opposite of the first case, or they can all be on the other side. Because the motion of these molecules are random, all of these are actually possibilities. The probabilities may be different for them, but they are still possibilities. So this gives us a total of 4 different microstates here. Right? If we have 3 molecules, now you see down here, we have a total of 8 possibilities. So the number of microstates possible is equal to 2 raised to the number of molecules or components in this system. So if we have 10 atoms, as you may be able to see down here, then the number of microstates would be 10 or 2 to the 10th, or 1024. If we have a mole of atoms, then the number of microstates is 2 to Avogadro's number, which is a very large number. So the more particles we have, the greater potential for number of microstates, which means the greater potential for disorder. Right? So we're really looking, when we're comparing these entropy changes, we're really can think of it in terms of microstates. Right? Are we increasing or decreasing the potential number of microstates? Or which is a reflection of the disorder or potential disorder of the system. All right. So let's take a step back then and see how this is going to be affected by various parameters. So entropy depends on temperature. So we think about energy and movement. As we increase the temperature, we add more energy to the system, particles begin to move. Right? We can change something from a solid where they're sort of vibrating next to each other, into the liquid where they're moving around, into the gas where they're separated from each other by great distances. So as temperature increases, the potential disorder is also going to increase. So it is directly proportional. So as temperature increases, the entropy, S, increases. Right? Which can be directly related to the physical state, as we saw earlier. Right? Things that are solid, the molecules are sort of locked into a certain position, which is going to be different than in a liquid where they can move around a little bit more freely, or a gas where they're very separated. Right? So as we increase the physical state, our entropy is going to change. The higher energy state, the gas is going to, again, then be higher in entropy than the more constrained or the solid. the formation of a solution is also going to affect entropy. So if we're taking two things that are not together, two separate things, and mixing them together, now we've added possibility for increasing randomness, if you wish, which is going to increase our entropy. So making a solution is going to change our entropy. And entropy is going to be related to size and molecular complexity. So the larger an atom is, it's going to change or larger a molecule is, then we're going to have an increase in entropy. Or the more complex that is, because we're going to change the effect, the way things are arranged is going to have. Right? But when we talk about these things, we're always comparing as close to the same situations as possible. So we're going to say the gas of one versus the gas of another, or a solid of one versus a solid of the other. Going between these states has a bigger effect than this sort of increase in complexity or size. Right? So let's look at this graphically. Two things. So this first one over here, we can see that we're taking a substance and going from a solid. Right? Notice that on this graph we have a zero value. So if we bring our temperature all the way to absolute zero, all motion therefore stops, which means our entropy will be zero. Right? As we start increasing the temperature, then the number of movement increases, so we see this increase in entropy until we get to the melting point. Now at the melting point, you may or may not remember that at the melting point we get a change in energy without changing the temperature. So we get this curve up here where our entropy increases, but we don't change temperature because we're going from that sort of fixed state into the mobile state. So as that occurs for all the molecules, we get an increase in entropy. Again, then in the liquid is going to continue to go up until we reach the boiling point. Now those molecules are going to separate in distance, which is going to allow a much bigger increase in entropy. And then it still can increase as the temperature increases, but it's a much shallower curve, right? So it's a much smaller change as we go from a solid to a liquid to a gas. We can see that same thing over here in this figure where we go from solid to liquid becomes more disordered, liquid to a vapor, more disordered. This one down here, you can see, is where we're going from a not mixed or solution where we have a solute and a solvent into a solution where we get an increase in disorder. So we see when we do that, we get this increase in entropy because we are introducing randomness through this solution. So let's just look at these couple of examples here and think about how the entropy is going to change as these processes occur. So if we condense water vapor, so we go from a gas phase where these molecules are far apart, and now we're bringing them closer together, which is going to decrease the randomness, right? Which means that our delta S, or change in entropy, is going to be less. Our initial state was greater than our final state. So finals minus initial gives us a negative change. So unlike the entropy values themselves, all the entropy values are going to be positive. We can get these, in the change in entropy, we can get a positive or a negative value. So if we form solid sucrose crystals from a supersaturated solution, so they're in solution, they're going to form a solid, where again we see a decrease in randomness, we get more order in our system, which means our delta S is negative, or entropy decreases. Heating a gas from 60 to 80 degrees Celsius, again, remember, entropy is related to temperature, so we increase the temperature, we increase the entropy, which means in this case, entropy is going to increase. And finally, subliming dry ice carbon dioxide. Subliming, again, remember, is going from a gas to a solid, or excuse me, the other way around, a solid to a gas. So we're going from fairly ordered to a very disordered system, so our entropy is going to increase. So these are the types so we're going to be talking about how to actually calculate these values with numbers next time, but really need to be prepared to think about it in this way.